Hi and welcome to our last class. Today we have an exam review session and I go through some basic information about our final exam, and also we have a number of examples that you have seen them before, but I have them here back to back so that you can access them more easily. Your exam will cover chapter 7 and 8. Chapter 7 is on signalized intersections. Chapter 8 is on traffic demand forecast. The exam is on May 3rd at 3:30 p.m. in Moodle. This is the exam date that is given to us by the university, so we are not making any change there. We have 1.5 hours for the exam, so be mindful that the exam exactly opens at 3:30 and then it closes at 5. We will have 4 or 5 questions, and all rules that we have here are identical to our previous exams. So you would not expect anything different in terms of the format of the exam in the last exam that we have. Similar to previous exams, you can bring any calculator that you want. You are not allowed to use your cell phone. The exam is closed book and closed notes, but you're allowed to bring a leather size cheat sheet to the exam. You can write on both sides and you can put anything that you want on this cheat sheet except for answers to a specific question. Any table that you need, I will give them to you. I will not providing any equations, and the role of your cheat sheet is to, one of the roles of your cheat sheet actually is to provide all the equations that you need on the exam. So let's now go through the examples that we have and have a better idea of what we can expect on the exam. I'm going to go through 4 example problems in this video to give you a good idea of what you're going to see on the exam. There's going to be one difference between exam 2 and 3 on Moodle. On exam 2, I ask you to upload your answers separately for each part of a question. I think that needed a lot of time for you guys to take photos and upload. So what I'm doing is that now for each question, you just put answers, upload the answers all together. So what you'll be doing is that on a piece of paper, you write your solution approach and the final answer. And so you do it for part A, B, C, D, and you just upload everything together. Very similar to questions 1 and 2 on your previous exam, not similar to question 3 and 4. Okay, so that means that rather than taking photos many times, you just take one photo for each question and then a photo of your cheat sheet. So here's the first problem. It's a problem from chapter 7, signal timing optimization. So in this problem, the phase sequence is given to us in this figure on the left. You can see that this is the phase sequence. On the exam, I'm going to give you the phase sequence. Also, on the right hand side, you see the volumes. So you see these numbers. So always in the order, the first number is going to be left turn, then through traffic, and then right turn. So here I have these order for each of these numbers. So left turn, through right, left turn, through right. So find control delay and level of service for eastbound left and eastbound through movement. So this is an example that you see like a maybe in the class or on a homework problem, but on the exam, I'm not just going to ask you to do everything and show me the final delay. You're going to see a lot of steps, and I'm going to go through these steps, but in the exam, just be ready that it's going to ask you, for example, for you to find the minimum cycle lengths, find optimal cycle lengths, and based on that, find green times and delays, and I'm going to ask all of those in the sequence. So let's take a look at the solution to this problem. So this is still input. So the adjusted analysis flow rates are given to us on the figure. Also, we need to know the adjusted saturation flow rate. So those are given for eastbound left and westbound left. They are 1800. For eastbound through right, 3450. Westbound through right, 3500. For northbound left turn lane group, it is 500. Southbound left turn, 350. Northbound through right, 1800. Southbound through right, 1800. So what we need to do, if you want to find the delay, first you need to find the cycle lengths and green time. So I'm going to go through the process of finding the cycle lengths. And if you want to find the cycle lengths, you need to know what are your critical lane groups. Based on that, you're going to find the cycle length. So I'm going to go through finding the critical lane groups first. So I'm going to do that for each phase. On phase 1, we have eastbound left and westbound left. The flow rate is 220 for eastbound left. Saturation flow rate is 1800. So that gives me analysis flow rate to saturation flow rate ratio of 0.122. For westbound left, that is 0.139. So between the two lane groups that I have in phase 1, westbound left is the critical one. On phase 2, I have eastbound through right and westbound through right. If you just do the math, you would find that the ratio for westbound through right is 0.271. That's going to be the critical one. On phase 3, we have 4 lane groups that are going together. So northbound left, the ratio is 0.14, southbound left 0.143, northbound through right 0.294, and for southbound through right it is 0.25. So here you see the critical lane groups that I have, and I'm going to go with this. So the next thing that needs to be done is to find the summation of these values. So that summation, I'm finding it here, it is 0.704. And also we are going to assume a critical intersection x sub c ratio of 0.8. So you can make this assumption on the exam, but because I want the solutions to be similar, I'm going to give the value of x sub c to you on the exam. So one other thing that needs to be done is to find the total loss time at the intersection. So in this intersection, all the information that we have is that we have a total of 4 phases. A total of 3 phases, and nothing is given to us for loss time, so we're just going to assume that loss time per phase is 4 seconds. Whenever it is not given to you, you assume that it's 4 seconds per cycle. So with all that information, now we can find the minimum cycle lengths. So the equation is L into x sub c divided by x sub c minus the summation of v over s ratios. Everything is given to us. So the minimum cycle length in this problem is 100 seconds. So now I can go forward and find green times based on this cycle length. So I have several options. I can use minimum cycle lengths to find green times. I can use optimal cycle lengths to find green times. There might be another cycle length that is given to me to find green times. If I go with any number other than the minimum cycle lengths, I'm gonna have to update the x sub c value. But here we are going with minimum cycle length, and this is really your choice. What is suggested is to go with C optimal, but in this problem we are going to go with C min, so you don't need to update x sub c. So then finding G1, G2, or G3 is just multiplying the V over S ratio by cycle length to x sub c ratio. So you can see that G1 is going to be 17.4 seconds, G2 33.9, G3 36.8. If I add all those numbers plus the loss time, which is 12 seconds, I'm going to get to 100.1. It's almost 100 seconds, so it means that I did all the calculations right. Remember, if I ask you to use a different cycle, and that's what is going to happen on the exam. So if you find minimum cycle length, and then I tell you assume that the cycle length is, for example, 120 seconds, and find G's, then you need to update X sub C. Okay, now that we have determined the cycle length and green time for each lane group, we can start finding delay. So I'm going to start with finding delay for eastbound approach. If you remember, for eastbound approach, I have two lane groups. First lane group is left turn, and the other one is true and right. So first, let's find delay for a left turn lane group of eastbound approach. So we need to know what is G over C. The G that we calculated was 17.4. Cycle length is 100. So you find G over C as 0.174. We need to find C, small c, or capacity. So that's saturation flow rate multiplied by G over C. Saturation flow rate was given as 1800. If you multiply it by G over C, you get 313.2 vehicles per hour. That would be the capacity that we have for our left turn lane group. So we only have one lane. It is going to be 1313.2 vehicles per hour per lane. You need to find V over C. So V was 220 divided by 313. That's going to give you a V over C of 0.702. D1 is 0.5 into cycle length, 1 minus G over C square. So G over C was 0.174. 1 minus minimum of 1 and V over C. So minimum of 1 and V over C is equal to minimum of 1 and 0.702, which is 0.702. So that's how I get this 0.702 here. So you multiply it by 0.174. D1 is 38.9 seconds on average for each vehicle. Now we are going to find random delay, or D2. T is the duration of study period. If nothing is given to you, T is going to be 15 minutes. That's the case here. So it needs to be used in hours. So it's 0.25. X sub C is the same V over C. X sub I. And it's good that I made that mistake. So you want to make sure that X sub C and X sub I are two different things. X sub C is what is the slack value that we come up for the intersection. X sub I is V over C for each lane group. So X sub I is going to be V over C for left turn on eastbound. So it's 0.702. K is 0.5 because it's a pre-timed control. I is 1, isolated mode. We found C on the previous slide is 313. So D2, if you do all the math, is going to be equal to 12.4 seconds. When we have D1 and D2, and we assume that D3 is equal to 0, we can find the average delay for eastbound left turn. It's going to be 38.9 plus 12.4, or 51.3 seconds per vehicle. Now, this is going to give us a level of service of D for this lane group based on the table that we have that gives us the level of service based on the delay. Let's move to finding the delay for eastbound through approach. So again, we need to go through everything. I'm going to go a little bit faster. G over C is 33.9 over 100. C is going to be S into G over C. So the result is going to be 1169.6. vehicles per hour. V over C is going to be 880. That's the given flow rate divided by the capacity is going to be 0.752. If you do the calculation for D1, you're going to get 29.3 seconds on average per vehicle. For D2 on this lane group, everything pretty much is similar to what we had. So we have X sub I or V over C. So we just put everything in the equation. It gives me a D2 of 4.5 seconds. If you want to find the total delay, it's going to be 29.3 plus 4.5 or 33.8 seconds. And if you go to level of service delay for eastbound through right approach, it's going to give you a level of service of C. So at this point, we have found level of service for eastbound left and eastbound through right. What I can do in the next step is to find the average delay for total eastbound approach. And I do that by finding a weighted average of delays among these two lane groups based on the volume that they have. So to determine the average eastbound approach delay, we need to know eastbound left turn flow rate. It's 220 vehicles per hour. The eastbound left delay, we found it to be 51.3 seconds. We need to find eastbound through flow rate. It is 880 vehicles per hour, and eastbound through right delay is 33.8 seconds. Average eastbound delay is going to be the weighted average of those delays based on the volume. So it's 220 into 51.3 plus 880 into 33.8 divided by 220 plus 880. That's going to give us an average delay of 37.3 seconds. And if you look at the table, we are going to be on this range, and the level of service is going to be D. Okay, let's move on to the next example. Let's focus on our second example. It is coming from chapter 8. So we have a model. We are using a Poisson regression model to estimate the probability of shopping trips. The model is given to us here. You see that B sub zi is equal to negative 0.35 plus 0.03 into household and blah blah blah. So given that the household has 6 members, annual income of 50K, and they live in a neighborhood with a retail employment of 150, what is the expected number of peak hour shopping? And what is the probability that the household will not make a peak hour trip? Okay, so let's go over the solution of this one. What we need to know to do first is to find lambda I, or expected number of trips. So what you need to do is to put everything in the BZI equation, and lambda is going to be equal to e to the power of BZI. So it's going to be e to the power of negative 0.35 plus 0.03 into 6 plus 0.004 into 50 minus 0.1 of 1.5. That is going to give us an expected number of trips equal to 0.887. Now keep in mind that it is okay that this is not an integer number. This is expected number of trips, but now we can find the probability of having 1 trip, 2 trips, and 3 trips, and so forth. Now, the question asked about the probability of not making any trips. That means that we are talking about probability of t equal to 0. So if you want to find that, it's e to the power of negative lambda I to the power of 0 and 0 factorial. So it's going to be 0.412. If you are asked what is the probability of making between 5 and 7 trips, you need to find P of 5 plus P of 6 plus P of 7. Very similar to what you did in chapter 5 for finding the probability of a certain number of vehicles arriving a certain location. So it's pretty much the same concept. So let's take a look at problem 3. We now here focus on mode choice. the problem is giving us 3 utility functions, and it's asking us if we have 4,000 workers, and the cost of driving is $6. Travel time is 20 minutes for car. With the bus, the cost is $1 and travel time is 25 minutes. And if for sharing a ride, they just divide the cost, so each of them are going to pay $3 and the travel time is going to be the same, 20 minutes. What is the probability of driving alone, sharing your ride, or going with the bus? So what we need to do is to find the utility values for each of those, find the probabilities. Actually, it asks about the number of people that are gonna take each mode. So you need to multiply those probability by the total number of people there, which is 4,000 workers. So let's do that. So utility of driving alone is 0.4, utility of sharing ride is negative 0.4, and utility of a bus is negative 0.45. So from here you need to know that the probability of driving alone is going to be the highest, then it's going to be the probability of sharing ride, and the lowest probability of is the probability of going with the bus because of the utility. So the highest utility is with driving alone. So let's find the probabilities. Probabilities of driving alone is going to be 0.533, sharing ride 0.239, and going with the bus is going to be 0.228. The number of people, you need to just multiply each of these by 4,000. That's the total number of commuters. So if you do that for driving alone, you find 2132. For sharing your ride, you find 956. And for going with bus, you find 912 trips. So let's move on to the next example here. Okay, let's start working on problem 4. This is a user equilibrium traffic assignment. So we have information about the number of people that want to go from point A to point B, a total of 4,500 people. We have information about route 1 and route 2, and we use this information to create link performance functions. And pretty much we want to find user equilibrium routes or flows, and we want to do that with a system of equations here. So let's first determine the link performance functions. We know that route 1 is 6 miles. We want to find the free flow travel time. So 6 miles divided by the free flow speed, which is 60 miles per hour, it gives me a free flow speed of 1/10 of a mile per hour. It gives me a travel time of 1/10 of an hour, or 6 minutes. If I do the same thing for route 2, the length is 3 miles, free flow speed is 45 miles per hour. It gives me a travel time of 4 minutes. So we know that on route 1, the travel time increases 2 minutes for every 500 vehicles. So it's going to increase 4 minutes with 1,000 vehicles, and x1 is in thousands. On route 2, it increases with the square root of number of vehicles in thousands. So it's x2 square. Okay, we also know that the flow that goes from point A to point B on those two routes is going to be 4,500 vehicles. X1 and X2 are in 1,000 vehicles, so it's 4.5. Now we need to make sure that both routes are used or not, and I'm going to do that on the next slide. So here I have drawn link performance functions for route 1 and 2. So you can see that if the volume is more than Q prime, and Q prime is shown here, both routes are going to be used. So our flow is 4.5, so it's definitely more than Q prime. But the way that we are going to do that is that we are going to put all the volume on route 1 find the travel time and then see if it's less than the free flow travel time on route 2. If it is, route 2 is not going to be used. If it's more than free flow travel time on route 2 is going to be used. And we do that vice versa too for route 2. So let's do that. We put everyone on route 1. Travel time is going to be 24 minutes. We find that by putting 4.5 into equation for T1. And if we find T2 of 0, it's going to be 4 minutes or free flow travel time. So 24 is more than 4. If we put everyone on route 1, that's not going to work. Someone is going to go and use route 2. We do the reverse. We put no one on route 1. We are going to get 6 minutes of travel time. We put everyone on route 2. We get 24 minutes. So we are not going to have a case that only route 2 is going to be used. So both routes are going to be used. If that is the case, now we can set up our system of equations. We can say T1 is equal to T2. We know that T1 is 6 plus 4x1. We know that T2 is equal to 4 plus x2 squared. So our first equation is going to be this. The second equation is going to be x1 plus x2 is equal to 4.5. Now, one of the mistakes that I have seen is that some students say x1 is equal to x2. That is a mistake, okay? T1 is going to be equal to T2. So if we do that and we solve that system of equations, you get x2 equal to 2.899 and x1 equal to 1.601. If you find travel times, this is the example that you have seen before. They're going to be 12.4 on each route. We can solve this problem by using the mathematical approach. So I'm going to do that here. Again, we know that T1 is equal to 6 plus 4x1. T2 is equal to 4 plus x2 squared. So I want to go with that and see how that's going to work. So first thing that I need to do is to construct s sub x function. I'm going to do that. It's integral of 6 plus 4w dw from 0 to x1 and integral of 4 plus w squared dw from 0 to x2. I'm going to substitute x1 by 4.5 minus x2 and just do the math. The function is going to be something like this. It's only based on x2, so I'm going to take the first derivative, say it equal to 0, and find the value of x2. So if you do that, you take the first derivative, you're going to get the equation here. You find, or you solve that equation, you get x2 equal to 2.899 and x1 is going to be 4.5 minus that. So it's going to be the same answer that we found in the previous problem. So the last example is about the system optimal traffic assignment. So again, I have this slide from your course here. The difference is this function that we have here. We don't see the integral anymore. So let's take a look at the example. It's the same example. We have the same link performance functions. And here what we need to do is to find the system optimal flows. So you need to again find or construct the S function. So here it's going to be x1 into 6 plus 4x1 plus x2 into 4x2 squared. So if you want to know what that is, this one is x1 into t1 and the other one is x2 into t2, and that is really the summation of xi ti over all i's, which is equal to the S function. So we have that based on x1 and x2. What I'm going to do next is that I'm going to substitute x1 with 4.5 minus x2. So if you do that, the S function is now going to be only a function of x2. We take the first derivative, set it equal to 0. That's going to give me an x2 of 2.467 and x1 of 2.033. And if you find the travel times, you're going to be that they are going to be different. So travel time on route 1 is going to be 14.13 minutes, on route 2 is going to be 10.08 minutes. And if I compare system travel time under system optimal and user equilibrium, we're going to see the difference, and that's on the next slide. So you have seen this before, so I'm not going to spend a lot of time here. For the user equilibrium, the travel time is going to be 930 vehicles per hour, and I found that by multiplying 4,500 number of vehicles by the travel time for each vehicle, and I divided by 60 to convert it to hours. For the other one, I need to do it for each route separately. So on route 1, number of vehicles is 2033, travel time is 14. On route 2, the number of vehicles is 2467, and travel time is 10. I just divide by 60 to convert to hours. It's 893. And here you see the difference in total travel time for the system optimal and user equilibrium. So with that example, we conclude this class and also this semester. I hope that this class was helpful for you and you learned the basic and most important concepts in traffic engineering. I hope you have a successful semester and also hope to see you in other courses. Have a great one.